Okay, so off we go. Here's what we were talking about last time we had a lecture, right? Of course, last time we had an exam. So the big idea was, how do you do an integral on a curve in space? And we had to recognize that this is fundamentally a different question from every other integral that we've ever looked at previously. It's all dimensionally weird. Its dimension and the space it lives in's dimension, they're different, and we're just not prepared for that, right? So we decided that as such, we don't really like that domain. We view it as an image, right? And then that allows us to pull back and rewrite it as an integral on a better domain that we like. In this case, an integral on the t-axis. Okay, and details for how to do that, right? We talked through, and this is our formula, and we did several examples, you might say, and now we're going to pick up with an attempt to make yet another example of this same kind of thing. So let's suppose that we want to compute work, right? No big deal. We have a formula. In fact, we have an improved formula for how to compute work, right? The high school point of view on this is scalar force times scalar distance, and then there's an asterisk, which is, okay, well, they have to be pointing in the same direction, and if they're not, then you have to think about the blah, 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 bunch of talk, right? And we resolved that. All that business about these having to move in the same direction got resolved by just saying dot product. So this was our, again, significantly improved formula for work. Okay, great. So here's now another improvement we're going to have to worry about, because it remains that this formula requires that the force be constant over the entire displacement. That's just that's built into what this formula is. What if it's not? Right? And then likewise, built into this formula is that the displacement has to be over a straight line path. What if it isn't? Right? There's all sorts of situations where we move not in a straight line, right? Okay, so how do we deal with that if they aren't? So, for example, suppose our force not constant, such as in this picture here. Right? You can see those force vectors are all pretty significantly different. Right? And likewise, what if your displacement, what if it's not over a straight path, such as, again, in this situation right here, perfectly routine scenario. Maybe this is what the wind is doing, and as you drive along, you want to know how much work it's going to take you to oppose all that wind. Right? Perfectly reasonable. Or maybe this is a mountain road, and you're not fighting against wind, you're fighting against gravity. Right? Well, gravity pulls a different direction at different locations on the mountain. Downhill, of course. So, perfectly routine scenario that we're considering now, and this old formula doesn't hack it. So, here's what we're going to do. We're going to, roughly speaking, say we're going to chop the curve up into little pieces, right? We're not going to consider the whole thing all at once. We're going to look at each little piece separately, on which the curve is approximately straight. Not exactly, pretty close. Round off errors go away in the limit, our usual refrain. And on which, even though the force isn't exactly constant, it's approximately constant. It's an itty-bitty, teeny-weeny little piece of curve. Vector field doesn't have enough time to change very much, right? So the problem becomes a lot easier on each little piece, and just like every other such scenario we've considered, we're going to then add up over the entire curve. Okay, so we're going to do that momentarily, but we do have to first consider another complication. And here, keep in mind, is our curve. Right? This is the path that we're going to be moving over. But I have to recognize that the amount of work it takes to drive a mountain road is very different if you're going uphill versus downhill. The direction matters. Right? So that's a problem, and more to the point, this is an unfamiliar problem. Let's look back at every other application we've seen. This fence that we looked at last time? Does it matter if you paint the fence clockwise versus counterclockwise? No, it's the same area. It doesn't matter. Chop it up whatever way you like. Paint it in whatever direction you like. Who cares? Right? Likewise, if we're computing, let's say, the amount of mass on a bent wire, there's no notion of direction to talk about. It just is. Mass just is. Right? And likewise, the location of the center of mass, it just is. So, we have not seen this issue previously. So, the idea that we're going to answer this question with our existing scalar line integral tool, right, that has nothing in it that in any way accommodates for this clearly very fundamental aspect of this question is lost cause. Forget about it. It's not going to happen. Okay, so scalar line integrals will not do it. In order to get our hands on this, I'm going to define what we mean by an orientation. An orientation is just an indication on the curve itself of which direction you're going. Right? If you want to know how much work it takes to drive this mountain road, well, you've got to clarify with your question. Do you mean as I go uphill? Let's pretend that the direction that I have here is uphill on the mountain. Do you mean the amount of effort it takes to go uphill, or do you mean the amount of effort it takes to go the other direction along the curve, namely downhill? Right? So that's got to be part of the question. Said differently, we need for our curve to not just be a bunch of points. We need our curve to have this attached orientation. So we're going to consider now a completely new geometric object called an oriented curve. Not to be confused with a curve. A curve just sits there. Right? A curve is like a road. It just sits there. Roads don't really have a direction, right? You can put up signs and stuff, but it's a big chunk of pavement and it just sits there, right? An oriented curve is a curve with the attached additional understanding of which direction you're going. And that oriented curve has one direction. Okay, is everybody on board so far? Everybody see kind of why we need this idea and how we're at least labeling it. Okay. All right. Well, okay. It's going to be pretty familiar for the rest of this step. If you think about this one little piece of curve there, on that piece of curve you can talk about our displacement differential, dx. Right? That's on that piece of curve our, at least our linear estimate of how much our position changes. Linear estimate based on what's going on at this point right here. At that point, we're going in a certain direction. We're moving with a certain speed, right? And based on only that, our estimate of where we would be, dt seconds later is over here. Now we're actually over here. Fine. Okay, so it's not perfect, right? But again, round off errors are going to go away. It's not a problem. And then we also need to know the vector field, namely what is the force that I'm exerting as I move along that piece of curve. And again, it's not exactly constant, but it's an itty-bitty, teeny-weeny little piece of curve. It's approximately constant. Round-off errors are going to go away. And that's what we get then on this little piece of curve, that little piece of curve right there, on this I shouldn't say so. On this little piece of the curve C, that's the amount of work that it takes to traverse that little piece of curve. And then we're going to just declare that we're going to add that up. So I'm going to add up over the entire curve, whatever that entire curve is, right? We'll just say integral and add up all of these pieces. Of course, now we already have an existing formula for dw. dw is f dot dx. After all, on each little piece of curve, work is force dot displacement. Right? Chapter 1 already arranged. Okay, so this then is what we find ourselves looking at. This new expression, you will notice that it kind of looks like an integral. Right? But it's pretty different from any integral we've ever seen before in some creepy ways. Our integrand what I'm going to call our integrand, right, is a vector field, right? And that's unfamiliar. We've not really seen such a thing before. And then even worse, our differential is a vector differential. It's the dx vector. It represents change in position. That's a vector change in position. So definitely different. Now it's, look, it's still a line integral in the sense that we're going over a curve and, linguistic flexibility as before. But again, fundamentally different. We have a vector integrand and we have a vector differential, and thus the term vector line integral. Okay. Believable? Okay. All right. Now, you might be worried at this point that, oh my gosh, we have a clearly more complicated idea. It's a more sophisticated idea. This isn't scalar times scalar equals scalar anymore. This is an integral that has vectors and dot products and orientations, all these new ideas that it was just a little intimidating. Seems like this might be hard to compute. Here's the good news. It's actually super easy to compute these. I would pose it is easier to compute these than it is to compute scalar line integrals. And I'll clarify on that in a minute. To support all of this, let me remind you, all this right here is a flashback from Chapter 3, Old News. We talked about on any given parametrized curve, there's a little piece of curve. You can talk about its length, ds. You can talk about its displacement, dx vector. You can talk about the unit tangent vector, the velocity vector, which of course is the derivative. All that's, again, established old news. And further, remember we talked through these formulas right here. This is also established in Chapter 3. That we have these different formulas for how to compute the dx vector. And with all that in mind, notice all I've done down here is just rewrite the dx vector in, you might say, 2 additional ways using these 2 formulas for how to compute the dx vector. Everybody on board? And we're done. We have, for example, if you want to do the pullback of an integral defined on our parametrized curve, you want to instead pull back and do an integral on the t-axis, boom, there you go. There's your pullback. Your new domain is just going to be the integral from a to b, whatever defines your range of values for t. On the t-axis there, and again, off you go. We're about to compute an example. Is everybody with me so far? Okay. All right. Now I will elaborate on one additional thing before we go into the example. I claim that these are even easier to compute than scalar line integrals. And let's go back real quick. Again, reminder: we talked about this formula last time for how to compute a scalar line integral, and here's the sticky wicket. This integrand has a magnitude in it. Magnitudes are square roots. And when there's a square root in my integrand, I tend to not be happy about that. Right? Every so often you get lucky and it kind of works out nicely. But as we saw in this example right here, this magnitude was a square root. That square root is in our integrand, and that's why I don't like it. Right? And so, not happy about how that integral. That's going to be a hard integral to compute. Whereas, by contrast, where am I? Yeah, look at what we have here. This integral that we're going to compute on the t-axis, there's vectors. Yeah, sure, but then you just dot them. No magnitude to be computed. It's awesome. Very handy. Now, fear not, the magnitude's in there, right? That's part of what makes the x prime vector what it is. The x prime vector has the speed wrapped up in its magnitude. You just don't need to compute it. So this is purely a sort of a streamlining of the process. It's not actually disappearing. Okay, so let's see an example. Let's get a one under our belts. Here's the question. We have wind exerting forces on us, and we want to walk along a certain path, and we want to see exactly how much work does it take us to move along this path while resisting the force that the wind is exerting on us. Okay, and this is going to be a largely plug and chug example. There is one little twist that we have to be careful about, and that is forces are awkward. Forces very often have sort of equal and opposite sort of complementary forces associated with them. So, for example, let's take my stylus here. It has a certain amount of weight. Weight is a downward force. And yet, my stylus is not accelerating downward. And why is that? Well, because I'm pushing upward, right? And the fact that my stylus is not moving means that the downward force of gravity is being exactly opposed by an upward force generated by my hand. Does that make sense? So this is what we mean by equal and opposite, kind of a physics idea. Anyway, so which of these two forces is the one that you want? Which force do you use to compute the work that you are going to exert? And there's a real easy answer to that question. If you want to know how much work you exert, you need to talk about the force that you are pushing with. Right? So notice in the phrasing of this question, the wind is exerting that force called F. Now, I'm not going to be exerting that force. I'm going to be exerting the opposite force. Because if the wind is blowing this way, I push opposite of that so it doesn't blow me over. Right? So I'm going to be pushing with the force negative F. And since the question is about the work that you exert, not the wind, right? We're going to pick that opposite force, and thus that minus sign right there. Everybody on board? Questions? Everybody's happy? Okay, so everything else is plug and chug. And so let's see here. Apparently we're going to have to parameterize our curve. Now we do have to think about this a little bit. The top half of the unit circle, let's do it like this. The unit circle I parameterize with our old familiar formula right there. There's the unit circle. Wait a second, I want just the top half of the unit circle. Well, the top half means I'm going to look just for these values of t. All right, I don't want to go all the way around this unit circle. I'm interested just in the top half. And okay, so there's my parameterization. I can see right here in my formula, my computational formula, if you want to compute a vector line integral, you're going to need to parameterize and compute x prime to plug in. So let's go ahead and do that. All right, we take the derivative. No sweat, easy to do. And now it's just a matter of plugging in. So our original integral is this. Let's see here. Our vector field was given to be that. Let's see here. Our dx is x prime dt. Our x prime we computed already. X prime on the previous page was that. All given. Right? Now, what are we going to do about the x and the y over here? What am I going to do with... Oh, gosh, I'm running out of colors again. Guess I can use dark green. What am I going to do about this y right there? What is y? Don't forget, the parameterization is what tells you that, right? Right here. The whole point of the parameterization is it tells you position as a function of time. And so therefore your y coordinate of your position is a given function of time. Well, given in the sense that we've already parameterized it. So y is sine t. And notice, let's see here, y sine t. Likewise, x cosine t. See, I'm just plugging in, right? I'm hardly doing anything. I'm just slowly and carefully plugging in for what I have. And let's see here. So now we, and of course, that minus sign that we put in because of the whole equal and opposite forces thing, don't forget that carries on through as well. It's easy to accidentally drop and, forget it at some point, so you just got to be careful. Okay. And then, check it out. You have yourselves a single variable integral. It turns out the integrand is nice and easy, and thus the integral is nice and easy, and answer done. What do you think? Everybody notice how plug and chug this is? Okay. All right. Okay, so now good news. You may recall we were worried long ago when we first wrote down scalar line integrals. We were looking at this expression here or the analog of this expression, and we said, hey, this is something that's intrinsic to the curve, but this appears to depend on the parameterization. Wait a minute, why should the parameterization matter? Or does it matter? And it turned out that it didn't, right? And again, not something we're going to prove in this class, but that works out in, large category cases. Anything we're going to worry about. So we find ourselves here now with the same question. We have an expression representing a quantity that is intrinsic to the scenario, and yet our answer seems to depend on the parameterization, and we have to worry now, does that parameterization matter? Will I get a different answer if I parameterize with one parameterization and you parameterize with a different one? And this is a more delicate matter here. I'd love to be able to say, yeah, it doesn't matter, go crazy. Not quite. It kind of does matter at this point, but only in a way that we've already addressed. And so specifically, if your parameterization is going the correct direction, if it's, as time increases, if it moves you in the same direction that the orientation says you should be moving on that curve. Keep in mind, our curve is an oriented curve. It's not just a curve. Not just a road. It's not just a dumb collection of chunks of pavement, right? It has a direction associated to it. If your parameterization is going that same correct direction, then go crazy. Parameterize any way you want, subject to that one constraint. Okay, but if you parameterize the wrong way, you're going to be off by a factor of -1. You're going exactly the wrong direction. Each one of your little dx differentials will be pointing the wrong way, right? Okay, so on each little piece of curve here, you're supposed to go that way, but you were going that way. These vectors are exact negatives of each other. So in your integral, every term in your summation will be exactly the negative of what it should have been, and thus you'll get exactly the negative of the right answer. Okay. So let me write this down a little bit more precisely. This is just notation, right? Nothing to be creeped out by, but we're going to use a superscript minus sign as a notation to just say, same curve but going the opposite direction. Same curve but with the opposite orientation. It's just a notation, right? I think it's a very reasonable notation. The book uses this notation, at least for a while, and then they switch, which I think is weird. But anyway, so we're going to use that notation. And as we just discussed, if you go the wrong direction, you should get a wrong answer by a factor of -1. So everything that we have on the page here is what we've already said. This is just writing it down a little bit more formally. All right. Is that believable? Everybody happy with this statement? Okay. Okay, so now I am going to ask a new question. I'm going to give you three, kind of four answers to this question, three good ones, one bad one. And the question is, same as the previous example, just going the other direction, now going clockwise on the top half of the unit circle instead of counterclockwise. How do we deal with that? Okay, well, the first two methods I'm going to show you involve just parametrizing as we desire. Now, again, I need to go clockwise. How are we going to parametrize this path that goes clockwise around the unit circle? And I can't just write down cosine comma sine because, well, that would get me going the wrong direction, right? So here's a couple of ways that you can do this. Again, tools for your toolbox. Different scenarios might favor one or the other of these, but they're both good tools to have at your disposal. So here, my first idea is to recognize that if you're going clockwise, then this is what you might call t equals 0, and over here is what you're going to want to call t equals pi. Because if you're going clockwise, you start here, and then after a certain amount of time, you find yourself over here. So that means as if our t angle is actually that angle right there, which is perfectly fine, no problem. That is an angle. I can call it t. Okay, bad news. I can't do trig with that angle. That's not how trig works. Trig is based on, very importantly, trig is based on that angle, right? That angle measured counterclockwise, measured off of the positive part of the x-axis. That's just the deal with trig. So now with that noted, with that angle clearly being pi minus t, then writing down the position of this point up here is nothing to it. That point is just, missed the thing, cosine and sine of, well, this angle. Right there, which is pi minus t. And reminder, I do expect and assume that y'all have memorized your angle addition formulas. I know a lot of high schools kind of let that slide. That's not gonna work for engineers at Duke. So y'all need to know those angle addition formulas, and as such, this simplifies like that. Okay, so this gives you our first perfectly valid parameterization of the clockwise oriented top half of the unit circle. How are we doing? Everybody all right? All right, now here's another way to parameterize the exact same thing. Okay, so again, clockwise on the unit circle. And the argument goes like this. If you want to go clockwise on the unit circle, right? But recall, you already know how to go counterclockwise on the unit circle. That's an easy one. Counterclockwise on the unit circle is our old friend, cosine t sine t. So I have the green one, I want the dark blue one, and the relationship between those two different parameterizations is they are clearly reflections of each other through the y-axis. And y'all remember that whole business with reflections, right? So taking my existing counterclockwise parameterization, reflecting over the y-axis will give me the parameterization that I'm looking for, namely the clockwise parameterization. Let's take a moment on this. Everybody happy with that argument? If I just reflect the green one, then I get the blue one. Okay. Now, of course, reflecting is a pretty easy thing to do. The formula for that reflection is just going to put a minus sign on the x-coordinate. Nothing to it. Okay, so again, tool for your toolbox. Now, for this particular example, yeah, they're both pretty doable. They're both pretty straightforward. Keep in mind, this is not the problem that you're going to face in your future, right? In your future, working as engineers, you're going to have some other curve that's, it's going to be different. I don't know how it's going to be, right? So it may be in that scenario that this idea of understanding geometrically, explicitly what your parameter looks like might be the helpful point of view. Or maybe not, and maybe, again, who knows, the scenarios you might consider might be very easily understood in terms of reflections. Don't know. Of course, we get the same parameterization either way. You can plug in the same parameterization into the formula and plug and chug, and of course, then you get the same answer either way. Okay. Everybody happy? Yeah, question.
It can be a dumb question, but
it's okay.
Once we have like the parameterization in the direction, how do I know if it's in the same direction as the direction?
Yeah, well, so in this case, we're kind of lucky with the geometry, right? And so, for example, this, I can just think explicitly about it. Well, here I am at t equals 0, and I can just let t increase and just kind of watch the parameterization move, and I can explicitly just see the direction. Otherwise, if you're not so sort of geometrically fortunate, another thing you can do is you can take your parameterization. You can take this parameterization here and just compute its derivative. Right? The derivative will give you the velocity. Now you have a vector showing the velocity, and the velocity, of course, points in the direction that you're going. Yeah. Is that cool? Yeah. That's a great question. Okay, here's the third way to do it. And just kind of showing off how great this theorem is here. We already know how to do it counterclockwise, and it says right here that if you go the opposite direction, you're just going to get the negative of the otherwise answer. So here's how easy this could be. Going in this opposite orientation, C2, we first just recognize that we're now going on the same curve with the opposite orientation. We recognize that when you go the opposite direction, you just get the opposite value. And we've already previously computed that on the original counterclockwise orientation, the answer is pi. So with this minus sign, of course, continuing on, we get our final answer, which is that the integral we want is minus pi. So, nothing to it. Really cool to be able to just make a quick little argument like that. Is everybody cool with that? Any questions? Okay. All right. So here's the fourth option that some students like to do, and I don't really care for the following. It's I'll say this. When you're flush with options, you got a bunch of different ways to answer a question, then the bar needs to be pretty high for accepting sort of nonsense, kind of hand wavy, eyebrow raising, concerning things. And we have good options here, especially this last one. Kills it, right? So given how good of an option we already have, let's consider with a very critical eye the idea of, let's see here. Here, let me look at this right here. What if I were to argue instead, oh, well, I'm going the other direction, and while you're going the other direction, instead of starting at t equals 0 and ending at t equals pi, it's like I'm going backwards, in which case I'm starting at t equals pi, and I'm going to end at t equals 0, and I'm just going to imagine that time's moving backwards instead of forwards. Now, some students like this argument, and they likewise like to just cross out then these bounds and say, yeah, if you're going the opposite direction, then we're just going to have our bounds go from pi to 0. So I see this sometimes, but here's my complaint. Okay, we're making an argument now where time goes backwards, and all else being equal, when you have other options, try to leave time travel out of your argument. Right? It's very concerning. It's very eyebrow. It's very sci-fi. Wait, is that real? Can you do that? It brings a lot of ugly questions into your argument, right? And so, why would you feel the need to bring up time travel when all you have to do, as noted here, is just say, yeah, we're going the opposite direction, and we have a theorem that says that gives you a minus sign. You don't need the time travel argument, right? So please, I think it's a very bad idea to, again, make questionable arguments when there's a really easy one that achieves the exact same result without mucking up your argument. Is that believable? Okay, so now we're going to switch gears and take a different point of view on this. Now, recall we've talked about this integral. We've observed that this represents work. To be more precise, though, this gives us work if our integrand is representing a force, right? The whole idea of this being work was that we were looking at this as force dot displacement. So we only get this interpretation that vector line integrals compute work in this one very narrow, very specific interpretation that the vector field is talking about forces. And y'all will recall that is not our only use for vector fields, right? So we also sometimes want our forces to represent a fluid flow. Specifically, we want sometimes to have our vector field represent the velocity of the fluid, which may or may not have anything to do with a force, right? So no longer interpreting our vector field as representing a force. Now, what does this mean? It's not work anymore. Right? Velocity dot displacement has nothing to do with work. Velocity dot displacement, what is that even? Like, even from a units point of view, right? Is not clear. So we want to figure out how to make a reasonable interpretation of line integrals in this new sort of context. All right. And just as a reminder, we already have all this set up down here, and very convenient. I'm just copying it down here again just for kind of convenience of reference, if that might be useful for y'all. So don't forget we have the dx vector. We have representing a differential displacement. We have the velocity vector, which of course tells you how fast you're going in what direction. And we have the unit tangent vector that represents just the direction. Says nothing about speed, just direction. And they're all related, again, by the usual formulas. Again, old Chapter 3 reference. By the way, a good idea right about now to go back to Chapter 3 and remind yourself of why these are all equal. Okay. All right, so what are we going to do about this idea of fluids? And this is a weird argument that I'm about to make. Y'all have seen me do something kind of like this in the past. I'm going to ask a seemingly irrelevant question. A weird and seemingly irrelevant question. And you're going to wonder why we're doing that for, while we're doing the calculation. And then at the end, I'm going to have an answer for why we're asking the weird question that we're about to ask. And just as a little foreshadowing, the reason why is because the answer is going to give us this interpretation, believe it or not. Okay, so this is what we're about to address. So that noted, here is the weird question. Scrolling down to here. Not get too far ahead. So imagine that I have a curve oriented curve, going in a certain direction. Imagine then also that I have a kind of a volume that's around the curve. Right, so this is not just a one-dimensional curve. Well, the curve itself is, but I'm imagining this sort of thick. I call it a tube, right? But this kind of thickened version of the curve, you might say, but representing a bunch of volume that's close to the curve. Okay, and imagine that there's fluid in there. And if there's a bunch of fluid in there, and if that fluid is moving, then you could reasonably ask, and here's the question. Here we go. Looking at that fluid in this kind of tube sort of thing, to what extent is that fluid flowing along the curve? And I mean total, overall. I don't mean at a single point, right? But overall, over the entire length of curve, looking at all of that fluid that's kind of nearby. To what extent, overall, is that flowing along the curve? It's a weird question to want to ask. It comes out of nowhere, right? So don't look for why we're interested in this just yet. All right, well, so that's how we're going to address it. And I'm going to break up our stuff into a bunch of little pieces. Here's a piece of that fluid. Whose volume is easy to compute. Area times length. Right? Nothing to it. That fluid's going to have some velocity. Now keep in mind, I'm not actually interested in the actual velocity of the fluid, right? I'm only interested in the extent to which the fluid is flowing along the curve. So not the velocity itself, right? But the extent to which it's flowing along the curve, of course, is a component. And a component is, of course, also easy to compute, right? Components are computed with dot products with unit vectors. So for each little piece of curve here, this little piece of curve, there's a certain amount of volume that's flowing along the curve, a certain amount of a component, and so we'll just then add that up over the entire curve. And adding up over the entire curve, let's see here. Let me say, adding up over the entire curve. You get this expression down here, which I'll scroll up so we can see better. And the answer to our weird question that we don't really still understand why we're asking, our overall answer to the mysterious question is this right here. Okay, how we doing? Is everybody on board? Okay, so why do we care? Well, check it out. The thing we're actually interested in shows up as a huge portion of the answer. Right? So this vector line integral, it's a little bit off to say that it is Q. It's not Q, right? There's this extra factor of area here. But of course, you could imagine taking this factor of area, kind of dividing it over to there, and saying, well, okay, sure, but it's the fluid flow rate per unit area. Which, if you think about it, kind of makes sense, right? I mean, obviously, the bigger the cross-sectional area is, the more fluid there is. More fluid means more fluid to be flowing along the curve. So, obviously, this factor of, obviously, this area participates in the form of just being a multiplicative factor. So, this actually makes the question really more natural. The cross-sectional area was arbitrary. We don't want arbitrary stuff in our answer, right? So now we have, I'm going to say, an answer to a better question. We shouldn't really be interested in the total flow of fluid. We should instead be interested in flow rate per unit area. And flow rate per unit area is what this vector line integral ends up being the answer to. So really nice answer. This is ultimately the answer that we were looking for. Given our vector field being a fluid, velocity of a fluid, what the heck is this thing, vector line integral? The answer is total flow rate of fluid along the curve per unit area of cross-section. Okay. All right. How we doing? What do you think? Everybody good? Okay. Now there is a related idea. There's a special case that ends up being really important later on. And it's good to introduce this idea now. And that is, okay, if we are interested in a vector line integral, but if our curve is a closed curve. It's a special case, right? It's still a vector line integral. It's therefore still representing the extent to which the fluid is flowing along the curve, right? But the idea is that if it's a closed curve, then now we're not just asking the extent to which the fluid flows along some arbitrary curve. Now we're keeping track of the extent to which the fluid is flowing along as the curve kind of goes in a, I'm going to say circle temporarily. It's obviously it's not necessarily exactly a circle. Any closed curve will do. But all closed curves kind of have to loop around in some sense. Right? Certainly the tangent vector has to make a loop. Right? And so if we're measuring the extent to which the fluid follows along and around just like a closed curve does, then I think the term circulation is a reasonable term, right? We're measuring the extent, in some sense, the extent to which the fluid is going around. Seem kind of plausible? By the way, here's a real-world example that y'all, I don't know if y'all had, my dad always would go around the house talking about, hey, you got to leave this door open, or you got to leave this door closed because of circulation. Air conditioner circulation, right? And I don't know if y'all are familiar with how air conditioners work. It's just a process, right? But there's something up in the attic typically that gets really cold, right? And then air blows over the cold thing and then into the house. But then it has to be able to get back to the air intake so it can go back in again, right? You can't just pump cold air into a house. There's only so much space in there for the air. So the more air that you pump in to the house from the attic, well, some air is going to have to go into the attic from the house, right? And so when you have an air conditioner, the air is going around, well, and again, it's not a circle. It's going around some weird path, depending on the shape of the hallways in your house and stuff, right? But nevertheless, you're talking about a fluid flowing around basically a closed curve. And so literally the term circulation tracks, I think, very nicely with that familiar example. Does that make sense? Okay. All right, so let's just talk intuitively now, real quick. What would you figure in this case right here? Right? What would we expect about the circulation? Well, if your curve is like that, and if your fluid is like this, to what extent is the fluid flowing along the curve? Well, pretty substantially, right? The curve is going like that. The fluid is flowing along the curve, like almost exactly. So there's a lot of fluid flowing along the curve, and the fluid's going the same direction the curve is, so positive circulation. Okay, now, related example. Let's look at this case right here. Here now I have a new curve. This curve now is going the other direction, but the fluid is going the same direction it had been, So now, to what extent is the fluid flowing along the curve? And you might be tempted to say, well, yeah, check it out. Look at that fluid. It's going right along that curve there, right? There's the curve, and there's the fluid, and the fluid's flowing along the curve until you realize, yeah, but wait a minute, the curve's going the other way, right? And so the dot product up here is going to be negative because we're going you might say, the wrong direction, right? So here you would expect the circulation to be negative. Does that make sense? Okay. And then there are other questions where it's really just not clear. And so now you look at a case like this, and that curve, I mean, in some places the fluid is flowing opposite the direction the curve is going. But in other places, the fluid is going with the direction that the curve is going. So there's going to be, in this integral here, there's going to be some plus, there's going to be some minus. There's going to be, you really have to work out the integral to see what's going to happen there. And you can speculate for yourself about, where are the vector field stronger, and how long are the different parts of the curve. And you can form a good theory here, but it's not immediately clear. Last real quick thought, just for your consideration, if you were to imagine I like to imagine a leaf. Leaves tend to fall when they're dead, right? So here's my fall-colored leaf. Notice if this were to fall into a little rivulet or whatever, with the fluid doing this, notice that the fluid would be going around this way per the circulation, and what do you think this leaf is going to do? It's going to sit there and twist in the same direction that the circulation indicates. So this is a nice interpretation. It's just an interpretation. Don't overthink it. But circulation can be thought of as a way of sort of indicating which direction leaves will rotate in the water. Okay, see y'all later. Have a good day. Yeah, sure. See ya.